Hello everyone, welcome to Rock Slope Stability webinar, where we will be covering dips, RocPlane, SWedge and RocTopple. Before we start, we would like to wish you health and safety during this extraordinary pandemic. Just to let you know that most of us are at our homes and this webinar will be presented remotely from both Turkey and Canada. Hence, please let us know if you are having trouble hearing us or if the audio is bad. You may write to us through the chat box. You may also type your questions into the chat box and we will try to address as many as possible during the question period at the end of the webinar. Anyways, let's get started. My name is Yalın and I work as a geotechnical engineer and Rocscience representative at Geodestek. I will be with Angela Lee today. She works at the Rocscience Toronto office as a geotechnical software developer, and she is in the developing team behind the Rocscience Rock Slope Stability tools. Before we start, I would like to give you brief information about Rocscience. Rocscience is the world leading software developer for civil and mining industries. For over 20 years, Rocscience has built geotechnical tools used by more than 8,000 users around the world. Rocscience currently has more than 50 employees and more than half of them have advanced degrees in engineering. Rocscience's head office is located in Toronto, Canada, and it has offices and resellers around the world. Our software can be categorized under three subcategories, which are slope stability, excavation design, and geotechnical tools. If we quickly have a look at the evolution of Rocscience rock slope stability tools, RocTopple was initially released in 2013, while the previous versions of RocPlane and SWedge were released in 2014, and the DIPS version 7 was released in 2016. With the introduction of Maintenance Plus, the advanced maintenance service of Rocscience, those software were upgraded to the latest versions and equipped with improved features in 2019. The latest versions of RocPlane, SWedge, and RocTopple were released in 2019, and DIPS was released in 2020. Under the continuous software approach adopted by Rocscience, these software are receiving new features on a frequent basis, as well as the other Rocscience products. DIPS can be categorized under the geotechnical tools together with the software like Settle3, RSPile, RockData, and CPillar. Let's get started with DIPS. DIPS is a tool for geographical and statistical analysis of orientation-based data. It includes 2D and 3D visualization options by 2D Stereonet view and 3D Stereosphere view. The 3D Stereonet allows you to plot poles, planes, and contours in 3D hemisphere view, which is the basis for generating a 2D Stereonet. The 3D hemisphere can be rotated for viewing at any angle. This allows you to see the raw orientation data before projecting it onto 2 dimension. This is a valuable educational and analysis tool that provides an alternative to traditional 2-dimensional Stereonet. In DIPS, you can perform kinematic analysis of the joints using the orientation data taken from the field in order to determine if the slope you're analyzing is susceptible to planar or wedge type failure or toppling. Additionally, you can also view the strike density or frequency of your measured data using the Rosette plot included in DIPS. As I have mentioned, DIPS is our popular stereographic projection program for the analysis and presentation of orientation-based data. And by orientation-based data, I don't just mean the data of structural elements like discontinuities or joints, but you can also analyze any kind of orientation-based data and use DIPS in different areas of geology, such as mineralogy. The ones who have dealt with the manual Stereonets may recall we used to fix a tracing paper onto a printed out Stereonet using needles or pins and allow it to rotate. Then plot the grade circle and which corresponds to the true dip angle measured in the field by rotating the tracing paper. Or in most cases, poles of the planes, which represent the line that is perpendicular to the plane, were plotted for the sake of simplicity. But now dips allow the users to analyze and visualize orientation data following the same techniques used in the manual Stereonets. Thanks to the advanced technology, you can now analyze a large number of orientation data in just one DIPS file in just minutes. You can also define linear, planar, or curved borehole traverses to group data units according to the traverses on which the data was collected using the traverse ID, or to weight the data to correct for measurement bias by Terzaghi weighting. To combine data with different orientation formats, for example, dip direction and strike dip within the same dips file. Traverses are also essential for defining and processing oriented core data. If your data is from an oriented core that is formed of alpha and beta values, you can use dips borehole traverse option in dips to convert your data into dip direction or strike dip format. And if you have a curved borehole, then you can also have the option to define color and survey data to perform curved borehole analysis by simply splitting the traverse into approximately linear sections and define separate traverses for each section. By using the 2D Stereonet view, you can visualize pole clusters and density contours. You can also form planes and intersections. By using these options, you can ultimately perform kinematic analysis, qualitative and quantitative feature attribute analysis, and cluster variability analysis. As I have mentioned before, using the Rosette plot option, users can display a radial histogram of strike density and frequency of the entered data. But please note that the Rosette plot plots the strike of planes, not the dip direction of plates. You can always customize the Rosette plot by viewing Rosette plot view by navigating to the Rosette options dialog. Dips allow users to perform true and apparent spacing in a joint set, rock quality designation as RQD, and frequency analysis on the field data. To perform a joint spacing analysis, you must define at least one joint set, at least one traverse, and enable the distance column option in the project settings and enter the distance values. But for the RQD and frequency analysis, you don't have to define a joint set, but at least one traverse should be defined and the distance column should be enabled. One of the most used and beneficial features of DIPS is the kinematic analysis option. Users can perform kinematic analysis of the joints using the orientation data taken from the field in order to determine if the slope being analyzed is susceptible to planar or wedge type of failure or toppling. Please note that kinematic sensitivity analysis is a preliminary analysis that allows you to easily and quickly check for various rock slope stability failure modes by simply inputting the slope orientation, friction angle, and lateral limits. To perform a detailed limit equilibrium-based failure analysis on joints prone to failure, you should navigate to RocPlane, SWedge, or RocTopple. In these software, you can take into account the joint strength, shear strengths, water pressures, and any additional forces, if any, and perform detailed stability analysis. Kinematic analysis can be simply performed by defining the failure mode to be analyzed, and kinematic properties such as slope, dip direction, joint friction angle, and lateral limits. The latest version of DIPS includes new set versus set analysis option, which allows user to analyze the intersection of predefined sets when examining wedge sliding or direct toppling failure modes. The kinematic sensitivity analysis option allows you to define range of values for the slope dip direction, friction angle, or lateral limits, and generate sensitivity plots for each variable. This option allows you to display the effect of each variable on your kinematic analysis. The newly added polar chart type is also added to the latest version of DIPS. You can now plot your graph in a polar chart along with the traditional Cartesian chart. It is only available for the slope dip direction variable, and if you select the polar chart type option, all the other variables will be disabled. Before moving to our demo, I would like to briefly mention the newest features included in the latest version of DIPS. Dynamic data filter option has been added to allow users to create filters and to search for any subsets of data in a DIPS file. Kinematic sensitivity analysis has been improved to include set versus set analysis and polar chart type. 2D Stereonet view templates option has been added to save a template and load a predefined template, and the user interface has been improved. Now let's have a quick look at our DIPS demo. Let's go to the DIPS and start with creating a new file. I have my orientation data in an Excel file in a dip direction format. So I will basically just copy those and paste those values into DIPS. I click new and just paste my orientation data into DIPS. Then I will click to contour preset view to contour preset option to view the orientation data in 2D Stereonet view. Now, the first thing we should do in the Stereonet view is to check the stereographic projection type, where you can see it in the sidebar. There are two types of stereographic projection as an equal angle and equal area. Equal angle stereonets are mostly used in crystallography because the plotted angular relationships are preserved and can be measured directly from the stereonet plot, while the equal area stereonets are used in structural geology because they present no statistical bias when large numbers of data plotted. So I will change my stereographic projection type to equal area. And as the default hemisphere view is assigned as lower hemisphere in DIPS. In structural geology, the stereonet is assumed to be lower hemisphere projection since all the structural elements are defined to be inclined below the horizontal. This is unlike in crystallographic projections where elements may be plotted on either the upper or lower hemisphere, but we will continue with lower hemisphere. You can see that the contours are plotted in plot vector mode. In default, you can switch to deep vector mode by simply clicking on that button from the toolbar, but please note that the joint set defining options are disabled when you switch to deep vector mode. So it's more convenient to work in pole vector mode, and I will continue with the pole vector mode. Now I would like to define a filter and filter my orientation data accordingly. To do so, I will basically go to Analysis and Filter Options. I would like to define a dip direction filter, so I will rename my filter as dip direction. I will select the dip direction option in the data drop-down menu. I would like to filter data having a dip direction between 48 and 54 degrees. So I will select the operator accordingly and enter 48 degrees and click add. Then I will also click end. Then I will define the 54 degrees limit accordingly and press the add button. Now I can press OK and apply my filter. You can toggle between the filters using the filter drop-down menu. When I select the dip direction filter, you can see the filtered data accordingly. You can also export and import filters. I will go to the filter options once again. By using the little arrow button, where you can see on your screen, I will select import option to import a predefined and a saved filter. I will select my dip filter file, and you can see that it's been imported to my filter data dialog. Dip filter is defined to filter data having dip values between 22 and 37 degrees. I will click OK, and you can see the dip filter is applied to my dips file. You can also toggle between filtered data and unfiltered data. Now I will go back to the unfiltered data and define joint sets to perform set versus set kinematic analysis. There are three options to define sets in dips. The first option is to define a set window by clicking on two opposite corners on the Stereonet, as you can see on your screen. The second option is to draw a closed region around the contours using the pencil tool, as you can see again. Or the third option is to define a cone with specified angle by clicking on the exact location, which I'll be using. So I will define a cone having 10 degrees angle to limit the cluster size, and I will select the first and second sets and press enter. You can see that I've selected my two sets, and when I click enter, the major planes are already defined by dips. My two sets are now defined. Now I'm ready to perform my kinematic analysis, and to do so, I will navigate to Analysis, Kinematic Analysis option. I will enable the Display Kinematic Analysis option by simply checking the little box. My failure mode will be wedge sliding. Since we are working with pole vectors, the kinematic analysis option is already defined or defaultly defined in pole or pole vectors. My slope dip will be 60 degrees. Slope dip direction will be 25 degrees, and friction angle will be 30 degrees. I will select the set versus set from the intersection types menu, and you can see that my first and second sets are already selected in the set intersection dialog. If you define more than two sets, you can manually set either one of your sets as set A and set B. When I click OK, you can follow that critical intersections formed by these two joint sets are shown with red markers. You may have noticed that some of the markers fall within the red zone and some of them fall within the yellow zone. These two yellow zones located on the either side of the critical zone, which refers or identified with red zone, refer to the secondary critical zone. Critical intersections that are plotted in these yellow zones always represent wedges that slide on one joint plane. In these yellow regions, the intersections are inclined less than friction angle, but sliding can take place on a single joint plane which has a dip vector greater than the friction angle. You can also check the total number of intersections formed by these two joint sets, and number and the percentage of the critical intersections from the info section located just next to the Stereonet view. You can also toggle between the filter dropdown and check that kinematic analyses are also applied to the filtered data. You can see that I don't have any critical intersections since the data from joint set 1 is filtered. As you can see, there is no data from the joint set 1 because we have filtered those. Now Angela will talk about the RocPlane, SWedge, and RocTopple, and she will have a few demos of the latest features included in these softwares.
So as my colleague has mentioned, while DIP's kinematic analysis provides us good insight into the failure modes that are likely to occur, we need to utilize slope stability programs to perform a detailed analysis. I'll be covering the ROC slope stability tools, RocPlane, SWedge, and RocTopple. These programs apply limit equilibrium, taking into account slope and joint geometry, shear resistance, supports, and other forces in order to obtain a factor of safety. RocPlane is used for analyzing 2D planar failure, while SWedge is used for analyzing 3D wedge failure. RocPlane and SWedge are very similar programs in terms of analysis types and program features, with the main distinction being their geometry. In RocPlane, the failure plane is formed by a single joint plane, while in SWedge, it is formed by two intersecting joint planes. For the sake of brevity, I will only be covering the features in SWedge, while we note that essentially all the same features apply to RocPlane as well. To fully define your analysis in SWedge, the user must specify parameters related to the slope geometry, joint geometry, and strength parameters, as well as any additional forces acting on the wedge. The user can choose from 3 different analysis types: deterministic, probabilistic, and combinations. In a deterministic analysis, all input parameters for the wedge are exactly known, and one factor of safety is obtained. A sensitivity analysis can also be performed in deterministic mode, which allows us to vary one input parameter and see its effects on the factor of safety. In a probabilistic analysis, input parameters can be designated as random variables and assigned a statistical distribution. A probability of failure is obtained from the number of failed wedges divided by the number of samples. Probabilistic results can be displayed in a histogram or scatter plot for a number of parameters. Combinations analysis is something unique to SWedge. Multiple joint planes can be defined, and SWedge finds all possible joint combinations. Both probabilistic and combinations analyses provide us valuable insight into the likelihood of forming a valid wedge and the likelihood of failure. The bench design feature is an extension of probabilistic analysis in SWedge. Assuming either a constant bench width or constant interramp angle, you can input the design parameters and statistical information in order to optimize the bench design according to design constraints and field measurements. In a managed approach, the user is able to assess the number of failed wedges and minimum bench width required for each bench face angle. For quantitative analysis, the user is able to estimate the likelihood of forming different wedge sizes and the likelihood that such wedges will slide, which provides us an estimate of the probability of failure for various backbreak distances. Both methods provide us valuable information used for estimating the optimum bench space angle. In addition to self-weight and shear resistance, other forces can also be modeled. This includes supports, seismic forces, external forces, and water pressure. The user can select from a number of pressure distributions when modeling joint water pressure. The ponded water feature was added to the initial release of Maintenance Plus as a way of modeling the effects of water pressure acting on the slope faces. In most cases, this ponded water acts as a stabilizing force on the wedge. Since the release of SWedge and RocPlane Maintenance Plus, a number of new features have been added. Batch Compute and Automate from Excel can efficiently automate the computation and results generation for thousands of analyses. Improvements were also made to the bolt properties dialog, following that of Rocscience's Unwedge program. You can now assign a bolt type and bolt efficiency. You can now also save your defined bolt properties. As previously mentioned, ponded water was also added as part of Maintenance Plus. I will be showing a demo in SWedge of the Batch Compute and Automate from Excel features. The Batch Compute feature is useful for computing numerous model files and generating the analysis results. If we open up SWedge, go to File, Batch Compute, it'll bring up this dialog. To batch compute multiple SWedge files, select Add Files. For this example, I'm going to do a batch compute of the first 3 tutorial files that come installed with the SWedge program. Tutorial 1 is a deterministic analysis. Tutorial 2 is a probabilistic analysis, and tutorial 3 is a combinations analysis. So I'm going to select everything, and you'll see that these files are now added to the file queue. In the output file format, the user can select from either a comma delimited text file or Excel format as the file output. Here, I'm just going to select Excel, and I'm going to compute. As these files are computed, they will appear under the completed files. When the files are finished computing, they will appear under the same directory as your input files. So here in tutorial 1, if I open up the results, we can see that for deterministic analysis, we have one set of results for one specific wedge. For the tutorial 2 results, since it's a probabilistic analysis, you'll see that the results look a lot different. Here we have exactly 10,000 results, and this is because the file contains 10,000 wedge samples. Next, we will look at an automation example by creating our own sensitivity analysis using joint combinations. The automation feature can automate almost any numerical input parameter inside the input data and scale wedge dialogues. The first thing you want to do is define your model environment. Make all the desired selections inside the project settings, input data, and scale wedge dialogues. These selections will be used for all automation cases. Go to Analysis, Project Settings. For this particular example, I'm going to be performing a combinations analysis. Next, we'll look at the input data. I have defined my joint planes here. These dip and dip directions are not automatable. In fact, the same joint planes will be used for all automation cases. However, I do want to perform a sensitivity analysis by varying the joint water pressure percent filled. So I must go under here and ensure that my joint water pressure checkbox is checked. Then I want to start populating my Excel file where the automation inputs will be read in from. Go to File, Automate Compute, and we'll open up the Combinations Excel template. A blank template will appear, allowing you to input all of your slope, joints, forces, water, wedge scaling parameters. To save us a bit of time, I'll use a file that I've populated previously. So all my slope, joints, forces are all going to have the same values. The only thing I'm changing here is I'm changing the percent filled from 0 to 100%. And in this case, I'll have 101 cases. Next, we'll go back into our SWedge file. And we'll go File, Automate Compute, and Automate from Excel. You'll notice that this dialog is almost identical to the batch compute dialog. The only difference here is instead of adding SWedge model files, we'll be adding in our Excel template file. And likewise, as before, I'll output it to an Excel format. And same as before, as this is done computing, it'll appear under computer files. The results files will appear under the same directory as your input file. Here you have 101 output results. If I just open up one of them, you'll be able to see that 15 possible wedge combinations are formed, but not all of them are valid. After a bit of post-processing in Excel with the raw data from my Automate from Excel feature, I'm able to produce this plot. This plot represents basically a sensitivity of factor of safety versus percent filled for all my valid wedge combinations. And as you can see, as percent filled increases, my factor of safety decreases for all my wedge combinations. Now we'll talk about RocTopple. RocTopple is a 2D limit equilibrium program used for analyzing toppling failure. To fully define your analysis in RocTopple, the user must specify parameters related to the slope geometry, joint geometry, base and bedding shear strength parameters, as well as any additional forces acting on the blocks. External loads can be applied over portions of the slope as either distributed loads or line loads. Seismic loads can be applied by specifying non-zero seismic coefficients, which are applied over all the blocks. Supports can also be applied to the model along the slope faces. A new analysis method was added to RocTopple as part of Maintenance Plus. The block flexure toppling model is different to the existing block toppling model in that it considers shear failure due to flexure in each block. Again, I will be showing a quick demo in RocTopple of the block flexure toppling model. In RocTopple, under Analysis, Project Settings, Toppling Model, the default is set to block toppling. We'll leave it as is for now. Next, we'll go to Analysis, Input Data. Here you'll see fields to define your slope and joint geometry, point of force application, and base and bedding strength. Now we'll actually perform an analysis using the block flexure model. So we'll go back to the project settings and we'll change the toppling model to block flexure toppling. Now we'll go back into the input data dialog and notice that now the overall base inclination has been disabled. This is because in the block flexure toppling model, the overall base inclination angle is determined by the toppling joint dip. It is always perpendicular to that. Also notice that now you have this internal rock strength tab. The internal rock strength must be overcome to fail by flexural bending and shear. We'll leave everything as is. Now we'll do a comparison before to the pure block toppling model and now the block flexure toppling. You'll see that the factor of safety is very similar, but now there's this shear failure as well as flexural bending failure that some of these blocks are undergoing. And as we go into the input data dialog and we decrease the internal friction angle, you'll see that more blocks are failing under shear. That's the end of the presentation.
Thank you, Angela, and thank you all for attending. We would like to see you, hope to see you in our next webinars.